This playlist collects together and organizes the individual component modules, which together comprise our second lecture on categorical logic. We'll begin our lecture with a brief recap of the material that we covered in the first lecture. Recall that we analyzed categorical statements and determined that we could formulate our formal system, our representation of the underlying structure of these arguments, in terms of 4 standard form categorical statements, together with their denials. At this point, though I didn't emphasize it, we introduced an element of our translation heuristic. We noted that there are 2 different ways of understanding the classes related by this logic. There is the modern or Boolean interpretation, and there is the traditional or Aristotelian interpretation. The modern or Boolean interpretation makes no assumptions about whether or not these classes have members, whether or not these categories are empty, whether or not these properties have instances. It is equally a logic of minotaurs and round squares as it is a logic of houses and cars. The Aristotelian interpretation, in contrast, assumes that these classes have at least one member. It prohibits arguments about basilisks and Kei-Ming-Shao and focuses instead on arguments about animals and people and mountains and stars. We then developed our effective decision procedure, and specifically, we developed it to determine validity and invalidity for direct inferences, arguments that have a single categorical statement as a premise and that have a single categorical statement as a conclusion. We used Venn diagrams to graphically represent what minimally has to be true for the premise to be true and what minimally has to be true for the conclusion to be true, and this allows us to compare the conditions for the truth of the premises and the truth of the conclusion to see if the argument in fact is such that its structure guarantees that if the premise is true, the conclusion would have to be true. Once we're done with our recap, we will turn our attention to extending the reach of this formal system. We will do that by introducing more of our translation heuristic. We'll begin by modifying our logic to accommodate both the Boolean and the Aristotelian interpretations of categories. We'll see how we have to modify our Venn diagram technique, our effective decision procedure, in order to generalize that procedure so that we can determine validity of an argument in both Boolean and Aristotelian logic. Then we'll turn our attention to translation heuristics, rules of thumb that help us to translate a varied and complex language and world into this very simple formal system so that we can utilize it together with the effective decision procedure for maximum benefit. So let's start. Recall that when we first introduced our formal system, we looked at categorical statements. And we said every categorical statement has some measure of a quantity. And so we'll introduce 3 different standard form quantifiers: universal affirmative, universal negative, and the particular quantifier. They relate classes to each other. So that quantifier will talk about how much of the first class, which we always call the subject class, is included in or excluded from the second class, which we will always call the predicate class, and we'll tie our standard form categorical statements together using a single verb, are, or its negated version, are not. We use that to formulate our logic in terms of 4 standard form categorical statements. The universal affirmative statement here, all elephants are mammal. That's a type A statement. Our universal negative statement here, the type E statement, no planets are stars. Our particular affirmative statement, a type I statement, some mammals are chihuahuas. And our type O statement, our particular negative statement, some mammals are not chihuahuas. We said that we'll understand that second quantifier, some, the particular quantifier, as saying there is at least one member of our subject class. In order to decide whether or not direct inferences, arguments that had a categorical statement as a premise and a categorical statement as a conclusion, whether or not those arguments were valid arguments, we introduced our Venn diagram technique. So we said we would symbolize in our Venn diagrams what had to be true at minimum in order for each of our standard form categorical statements to be true. And we would do that by using 2 overlapping circles, one of them for the subject class, the other for the predicate class, so that this area here in the subject class and only subject class area, area 1, that would be where we put stuff that belonged to the subject class, did not belong to the predicate class. In this area over here, area 2, that's in the predicate class and only the predicate class. And that's where we put in any information that was just about the predicate class. This area, area 3, that's where we put any information about both classes. And this area here, area 4, that would correspond to anything about neither of the classes. And so to make that seem concrete, we talked about how the subject class could be our pairs of white socks. Predicate class could be our pairs of black socks. The intersection between our subject and predicate class could be our laundry day mismatching pairs of socks. And then that area 4 there could be the we forgot to do the laundry day where we don't have any socks at all. We then spelled out how we would symbolize each of our standard form categorical statements, what absolutely at minimum had to be true in the world in order for each of these standard form categorical statements to be true under that Boolean interpretation. So that maybe our subject class has a member, maybe it doesn't. Maybe our predicate class has a member, maybe it doesn't. And so we said our universal affirmative statement there, all ships are seaworthy vessels. If we want to symbolize what absolutely at a minimum has to be true, given that this sentence could be about ships, it could be about Pegasus, it could be about Greek gods, it could be about cars. Whatever it's about, what minimally would have to be true in order for that statement to be true. And we said, well, we're being good Booleans, so we don't know if there are any members of our subject class. We don't know if there are any members of our predicate class. But if this statement, all members of the subject class are members of the predicate class, is true, then what have to be true at minimum is this area right here. I'm a subject. I'm not a predicate. That would have to be empty because every member of the subject class is included in the predicate class. There couldn't be anything in here. And we would symbolize that by shading that area, turning out the lights, locking the door. There's nothing that can go in there. If this statement is true, that area has to be empty. Now, maybe that class has a member, maybe it doesn't. But what absolutely has to be true is that area, area 1, has to be empty. And the same thing for our universal negative. We don't know if there are any members of that subject class. We don't know if there are any members of the predicate class. But what would have to be true at minimum, in order for that statement to be true, would be that there couldn't be anything that is a member of the subject class and a member of the predicate class, because nothing that's a member of the subject class is also a member of the predicate class. So we would look at this area here, area 3, the intersection that's in both of those classes, that would have to be empty. That's how the world would have to be if that statement was true at minimum. And so we would shade that area. Area's got to be empty. We're going to shade it, turn out the lights, lock the door. There's nothing in there. When we went over to the particular statements, we said, with the particulars, it's going to be at least one thing. There's at least one thing. It's a member of our subject class. And in our particular affirmative, it's also a member of our predicate class. And so we say, okay, maybe there's 50, maybe there's 1, maybe there's 1,000,000. What absolutely at minimum has to be true? It has to be at least 1. We'll use an X to symbolize that. There's at least one thing. It's in my subject class. It is also in my predicate class. So it goes in this intersection here in both circles. That's what would have to be true at minimum in order for this particular affirmative statement to be true. Finally, our particular negative statement says, look, there's at least one thing. It's a member of my subject class. Got to be an S. It is not a member of my predicate class. Cannot be in P, so it has to go in S. Can't go in P, so we put our X right there. In S and only S. Now we said that's how we would symbolize what had to be true at a minimum in order for each of those standard form categorical statements to be true. Then we went and did the same thing for a premise or a conclusion that said my type A statement, all S or P is false, or my type O statement, some S are not P is false. Well, what would we have to do if our premise or our conclusion says that standard form categorical statement is false? And we showed how to do that. And then we saw that our effective decision procedure just simply created a diagram. This is what has to be true in order to make the premise true, and a diagram for a conclusion. This is what has to be true in order for our conclusion to be true. And then we used our our definition of validity. If the premise is true in a valid argument, the conclusion also has to be true. So we look at our conclusion and we go, okay, this is what would have to be true in order to guarantee that conclusion is true. What's in this conclusion diagram? That's got to be what's true about the world. And we look over at the premise diagram and we say, okay, this is how the world has to be if the premise is true. So if we made the premise true, would that give us what has to be true in order for the conclusion to be true? So is the information, is what we entered into the conclusion diagram also in the premise diagram? If it is, then the argument is valid. If it isn't, then the argument is invalid.